So next, let's be specific and explain the notion of the reduction, the definition of the reduction. So this blocks of text is talking about the reduction. So let me just read through that. Problem X polynomial time reduces to problem Y if arbitrary instances of that problem X can be solved using first the polynomial number of standard computational steps plus a second polynomial number of calls to oracle that solves problem Y. Right. So let's really just explain this very lengthy and this moment that's at this moment the a bit confusing statement. Right. So let's start with describing the problem X. Right. What do we mean by problem X? Problem X can be say the shortest path problem, and can also be say the say that the max flow problem, or something else. Right. Right. So let's say just at this moment we are really interested in the only that we are setting problem X to be the max flow problem, right? And similarly, like problem Y would be right. So you can talk about a problem, right? The problem Y maybe it's right the mean cut problem, right? At this moment, let's just assume this is our problem Y, right? So basically the message here, or the high level message I'm trying to deliver here is that when you talk about problem X, right? So it's not really one or two particular problem you are facing, right? It's not the problem in the English sense, right? The problem is really in the sense that it's a category of problems that you need to solve, right? Such as the shortest path problem is or such as the max flow problem, right? So let's say what should I do? So now let's just continue the discussion here. So we say that if arbitrary instances of problem X can be solved using like step number one, number two, right? So there's another notion here, definition here would be the arbitrary instance of problem X, right? So now let's assume that we are working on the as we said we are working on the problem X is the max flow, right? So now let's say this is the max flow problem. Max flow problem. Right? An arbitrary instance of the problem basically means that it's you need to solve a concrete max flow problem, right? So basically you are given G and the graph and the capacity, and then given these two the piece of information, and you need to be able to find the max flow problem, right? So when we have a very specific instance here, it's called an arbitrary instance of problem X, right? And this I think these are really some of the most important concepts in this definition, right? So now let's say that we need the two properties here. The first top property would be polynomial number of standard computation steps, and second property would be the polynomial numbers of calls to the oracles that solves the problem Y, right? So here is a pictorial example to highlight this idea, right? So let's say that the problem Y here is really the so-called mean cut problem, right? Mean cut problem, right? So an algorithm for problem Y basically says that let's assume that there just exists an algorithm. If you are given a specific graph and then capacity, you are able to with the black box is able to find the mean cut, right? This is the algorithm for Y. What the algorithm for Y means that basically that means that there's a black box that can solve any instance in this problem, right? And this reduction basically says that if it is possible that somehow I can sort of like start with an instance X, like instance of X, right? Say start with a max flow problem, right? When I say a max flow problem, that really basically just means that an instance of the max flow problem, right? That's characterized by G and C, right? G is the weighted graph, C is the capacity, and G is the directed weighted graph, C is the capacity, right? So let's say that the input of the max flow problem has this format, right? So the reduction basically says that if I'm able to tweak the input a little bit, right, and then fit, and then sort of like after I tweak the input, it becomes an instance that can be solved by the algorithm of the black box, and then we can tweak the output a little bit. And then after we tweak everything, then we are able to find the solution to the original problem of x. Then we say that the problem of x is Cook reducible to the problem of y. So now this whole discussion is still a bit abstract. So we will have to work through a number of concrete examples to really highlight this central notion of reduction. So don't worry too much if you are not able to totally understand either the meaning or the significance of the slide. Right. So in case problem x is polynomial time reducible to problem y, then we sort of write that the x is less than equal to y, like less than then there's a p and so a subscript p like after the less than equal to, right? So basically this is really just intuitively says that x is easier than y. And why is that? Why can we say things in this way if x is reducible to y? This is because that basically by looking at this figure, right, that we can sort of see that if we have a solver for y, this is a solver for y, right, then the solver can also be used to solve x, right? So that basically means that the solver for y is more powerful than the solver for x, right? And on and then you can sort of also think in this way, right? So more, let me write this as more powerful, right? So you can also think in the other way, right? So when you need a more powerful solver to solve a category of problem, the problem itself needs to be harder, right? So to put this whole thing in the context, that basically means that if my solver for y is more powerful, that means that the problem y itself is harder, right? So that's the reason that people write that x less than equal to y, right? So problem y is harder. That means that the solver for problem y is more powerful. That in this specific the context, that also means that the solver for problem y can be used to solve instances for problem x, right? And next, let's also take a look at this notes, right? We pay for time to write down instances of y sent to Oracle. Instance of y must be of polynomial size, right? So basically, so let's just go back to here, right? So there are instances of x and instances of y, right? So in our particular case, right, so the instance of x and y are really just in this particular example, they are just the graphs and capacities. So right, so the very same graph can be that needs a max flow problem can be used as the input for the mean cut problem, but in general it may not be true, right? So the problem y can say be what should I say, like be the set cover, right? Set cover would be another problem that you are going to see like later in this class, right? So set cover basically it's really just consists of a set of inputs that are related to sets and elements and has nothing to do with the graphs, right? The max flows input is graph, right? So but also, as you can see, that it turns out that the solver for set cover can literally be used to solve the max flow problem, right? So that basically means that max flow is easier than the set cover, right? In this case, when we do the reduction, then basically there's one center step here, right? So the input to the max flow here is really just a graph. But the algorithm for y accept another different forms of the problem, right? The problem, for instance, in the set covers is really just a set of elements, a collection of sets, right? A collection of sets. So basically at this moment you don't really need to know what is set cover, right? You just need to know that the input to the set cover is different from G, right? So but then we sort of need to leverage the solver for the set cover problem to solve the graph problem, right? So some sort of massage is needed, right? In order to translate G into an input format that's acceptable by the solver for the set cover, right? So and here and then after we do the translation, the input instances needs to be fed into the algorithm for y, right? So the notes here basically mentioned a little bit of the technical details, right? So that basically means that when we want to produce an instance that's acceptable to the solver for y, the instance itself can not be more than polynomial size. Let me just repeat. The instance itself has to be polynomial size, right? So when we start with a graph instance and we want to translate that into another instance that's acceptable by the algorithm y, then after the translation, the instance itself has to be polynomial size, right? The reason is that because we really have to write the entire instance out, and we also require, right, so in the definition we only require the number of steps that beyond the invocation of the oracle, right? So if I look at here and look at here, right, if I count the number of steps in these two green blocks, and then they should be polynomial step, or what's called, or we have been calling this polynomial time, right? And because we have to write out the entire input to the solver for y, and we only have polynomial time, right? So even we just keep writing, the input to the solver of algorithm y cannot be larger than the polynomial size, right? This is what this note is talking about. We pay for the time to write down instance of y, right? So we really have to, if you look at here, right, so we start with the instance of x and then translate that into the instance y, right? So we have to write down the instance before sending that to the oracle. So because we only have polynomial amount of time beyond calling the oracle, that can also tell us that the instance of y must be of polynomial size, right? So these are some a bit of the subtle details. Maybe you cannot appreciate this kind of details at this moment, but as you advance your own computer science career, or start your grad school, then start to look into this kind of problem again and again, then you will sort of be able to appreciate why this note is quite important, right? So again, like the x then less than equal to y and y less than equal to x is really quite, they are really quite confusing from time to time, right? So even if we just don't look at the definition and try to recover what the meaning of this two, like sort of like say, we sort of like, let's try to just recap, like without just looking at any of the definition, what is x less than y, right? So when we want to understand what's the x less than y, right, there's a solver for what, right? Is it an x or y, right? So this is the solver that is given, and what is the input? Input is x or y, right? So it turns out that the true solution here is that the input is x and the solver should be for y, right? So somehow like people just always get confused from time to time, the roles of x and y, right? So when indeed we are looking at this diagram, sometimes people just accidentally write y less than equal to x, right? For the reason maybe it's x is the instance from x is fed into the into the solver for y, so sometimes people accidentally write in this way, right? So this is the novice mistake, and again, like, this kind of mistake is pretty interesting. Now basically, I guess most of you have blank the feeling when I talk about this mistake, but when you start to do research and read a lot of the research papers written by your colleagues in the same field, you will be surprised from time to time. People always make make mistakes and confused by confusing x less than y with the y less than x, right? So next, let's just move into a number of quizzes. Like usually we don't do the quiz, but this kind of notion is really quite new, so we sort of need to take a bit of more time to internalize this the reduction notion, right? So let's just walk through this integrability quiz one, right? The first question is that suppose that x is polynomial time reducible to y right? So reducible. Sorry, like I still. So sorry, again, I sort of get confused, right? So again, like, so suppose x is polynomial time reducible to y, and which of the following can we infer? So which ones are correct? So here, then basically, let's just repeat probably the most important message in the previous slide. So x less than equal to y, you can literally interpret that as x is easier than y. So now with this kind of interpretation, we can now easily figure out which of these four options are correct, right? So the first option says that if x can be solved in polynomial time, then so can y, right? So it seems that this is contradict to the x is easier than y, right? So if x can be solved in polynomial time, we only know y is harder than x, right? So we don't know whether y is just a little bit harder or substantially harder, right? So it's not true that x can be solved in polynomial time, then so can y, right? Also that x can be solved in polynomial time if and only if y can be solved in polynomial time. This is also not true because it only says that x is easier than y, so it has not ruled out the possibility that x is strictly easier than y, right? So when x is strictly easier than y, then maybe one is solvable in polynomial time and the other one cannot be solved in polynomial time, right? This is also incorrect. The third one would be that if x cannot be solved in polynomial time, then neither can y, right? So this is getting a bit subtle, right? This is actually a correct one, right? So let's really just use this sentence to try to help us to understand why the C is correct, right? So basically, x is easier, but x still cannot be solved by using polynomial time, right? In poly, right? And then people believe, not people believe, right? So sorry that we are still not into the MP problem, right? And then people also have the knowledge that x the the y is harder, right? So even for the easier one, it cannot be solved in polynomial time. Then it's very likely that for the harder one, it also cannot be solved, cannot be solved in polynomial time, right? Right, so this is literally what the option C talks about. Like if x cannot be solved in poly time, then neither can y. Right, so this is also the correct one, right? And this is and A is incorrect, B is incorrect. And again, like if we just repeat the same argument, we sort of also know that D is also incorrect. So now let's move to the second quiz. The question asks that which of the following polynomial time reductions are known, right? So the first one is that if we want to so basically we look into two problems, right? The first problem is to find is the problem of finding the max flow in the graph, and the second problem is the problem of finding the mean cut in the graph, right? So here then we want to understand which one is known, right? So again, the idea here is to both get some intuitive understanding of the reduction notation, and together we also want to just internalize like the direction of the reduction. So right, so it's really just about being able to precisely understand the definition of the reduction, right? So let's start with the getting the intuition, right? So again, like as we described just now, right? So if we write a less than equal to b under p, then basically we said that a is easier than b, right? So now let's really just use this as our intuitive interpretation of the less than or equal to, and try to understand which of the options are correct, right? So the ground truth, right? So what we have known, right, from the lectures we did in the past 2 weeks is that the max flow, the problem, the so the if we have so basically it's that the problem of solving max flow, it's roughly the same as the problem of finding mean cut, right? So let's just recall that when we want to solve the max flow, we sort of you need to use the residual graph, and we keep updating the residual graph in every single round using the greedy algorithm. So when the residual graph start to become disconnected, then we find the maximum flow, right? And at the same time, at the moment the residual graph becomes disconnected, right? So let's just draw in this way, right? So I can also run a BFS starting from S, right? So the entire kinetic component would be A, right? So now the cut defined by A and the complement of A would be the mean cut, right? So basically that means that like if our so when we use our greedy algorithm, we can both find the max flow and mean cut. When we know the mean cut, and then by the by the duality theorem, we immediately know the max flow. And when we know the max flow, we at least also know the value of the mean cut, right? So then basically so with this kind of knowledge, we can sort of claim that in terms of the difficulty, max flow is as difficult as mean cut, right? So this is intuitively how can we interpret like the difficulty of these two problems in terms of the computational cost, right? So now if we have this message, like we know this, like we can now go back to the options and see which are one are the correct, right? So the first one says that the max flow is easier, right? Easier than mean cut, right? So easier. So this is less than or equal to, right? So easier or equally hard, right? Equally hard, right? So because of the what we see here, right? So basically the option A, like the choice A is correct. And for the same reason, mean cut is also easier. It's also true that mean cut is easier or equal to max flow, right? So both A and B are correct, right? So that's the reason that we need to choose C, right? So that's the how we intuitively interpret the meaning of this statements, right? So now we can also try again to look into the formal mathematical definitions, right? So let me just erase things a little bit. So now let's go back to the formal definition, right? So say let's really just try to understand what does this statement. We already know this statement is true, right? So and now we sort of want to use this reduction diagram to repeat what sort of solver is available and how can we call the solvers, right? So basically if this were true, then it's possible that there's a solver that's inside, and the input would be an instance of max flow, right? And the output would be, say, the value of the max flow, right? Flow, and the solver here would be the mean cut solver. Mean cut solver basically means that if there's a graph together with the capacity is given as input, say it will be able to output a value of the mean cut, right? Right. So now the question is that if I have a mean cut solver, am I able to use polynomial amount of steps that before calling this for solver and after calling this solver so that I can get the max flow, right? So now here the problem is that the way we solve this problem, right? So because A is true now, basically we sort of know that we can indeed do that, and in order to do that, the way we design the procedures that's right before invoking a solver and after invoking solver is very straightforward, right? We effectively really just need to do nothing, right? So the input is a graph and capacity. We don't need to tweak anything. We use exactly the same input and just feed that to the solver we have. And the solver gives us a number of the mean cut of the G and the capacity, like of the graph with associated with the capacity functions, right? So it will output a real value. We also do not need to manipulate the real values, and really just whatever output coming from the solver is actually also the output of our max flow, right? So basically, this is really just the the high level structure of what we are doing, right? So sometimes, right, so people have the different definition of the mean cut, right? So for instance, if the output, in case the output of mean cut is really just the set of A and B, it's not a real value. In case we see this kind of output, then basically we in order to design these two blocks, right, so we really need to do a little bit of extra things, right, in order to design these two blocks, right? So for this block, like basically we don't need to do any extra things, right? We just feed in the same graph to the solver, right? Now the solver output a set A and B, right? So as the mean cut, which is the mean cut of the input, right? So now we need to utilize this piece of information in order to compute the max flow, right? In order to use this piece of information, what we need to do is that we really just directly compute the value of the cut between A and B. And by using the max flow and mean cut theorem, the duality theorem, whatever value that's output by the cut computation, it's really also we know that it's also the max flow, right? So now when we compute the cut of A and B, this is the extra polynomial cost that's really mentioned in the definition, right? So polynomial number of standard computational step, right? So this is basically how we interpret this the statement that's over here, right? So let me make a last remark of the different types of reduction, right? So here we are looking at this at the polynomial time reduction, and then somehow we call that Cook reduction, right? Cook is a computer scientist that's sort of like come up with the notion of the NP-hard problem, right? So and his original paper talking about the NP-hard problem, right? So introduced this notion of the reduction, right? This is a computer scientist name, right? And there's also another type of reduction called the Karp reduction, right? So they are both polynomial time reduction, right? Sometimes we call that Cook, we call a type of reduction Cook reduction, and we call another type of reduction Karp reductions, right? So what's the difference between these two type of reductions? If we use the Cook reduction, we can sort of assume the black box we can sort of assume the black box can be invoked multiple times, and we are also allowed to do the post-processing, right? So basically, if you look back the definition here, right? So we allow our whole program that leverages the solver to have polynomial number of standard computation and polynomial number of calls to the oracle, right? So that basically means that for the same black box, where we are allowed to call this black box to help us to solve instances of its own type multiple times, right? But for the Karp reduction, it's not mentioned in this slide. It's a little bit more strict reduction, right? So it has two key differences, right? The first key difference is that we can only make one call to the solver. Right. Basically, the idea is that if I have to make a polynomial number of calls, right, more than one calls to the solver, then maybe it's also a sign that the original problem it's also quite difficult. So let me just elaborate this idea, right? So let's say that if we have x less than equal to y, right, and if in order to solve x, I need to make a polynomial number of calls to the solvers of y. So now it feels a bit unfair, right? So unfair in the sense that, well, it's indeed true that the solver for y can also be used to solve x. But at the same time, well, you need to call multiple times of y's solver in order to solve one x, right? So in order to solve one y, you don't need to call one time, and in order to solve x, you need to call, say, 100 times, right? So if we measure using this matrix, then it seems that it's not totally obvious that the problem of x is strictly easier than the problem of y, right? So the Karp reduction, right, intuitively tries to address this issue by not allowing invocation of the solver for multiple times, right? The second difference is that the carbon reduction also do not um, allow allow the post processing, right? Do not allow processing is really just means that whatever output that's coming from the solver, you are not allowed to do the extra manipulation. So it has to be output as it is, right? So it turns out that with this the two differences that's made in the the reduction makes these two types of the reduction very different, like in terms of performing the computational complexity studies, right? We are not going to talk about the different types of reductions for this rest of this course, right? So here is really just to give you a bit of the expositions that there indeed exist two types of reductions, and these two they may have different impacts in terms of the establishing computational complexity theories, right? So for the purpose of this course, right, so we can just stick to the easier Cook reduction.